going for a little different musical tone. That was the sound Silenced by Disturbed, first done by Simon and Garfunkel back in almost in my days. Alright, a little before my days, actually. I'm not that old. But, anyhow, so we were talking last time, we talked about waves, compressional, transitional waves, so forth, and we had gotten down to talking about frequency. We talked about how frequency is the inverse of wavelength. Alright, and basically the shorter the wavelength, the higher the frequency, because the waves are close together, and if they're moving the same speed, then frequency is always inversely related to wavelength. If you have long wavelengths and they're going at the same speed, then you will have a low frequency. If you have short wavelengths, moving at the same speed, then you will have a high frequency. So if wavelength is long, frequency is low. If wavelength is short, then frequency is high. Inversely related. There we go. All right. Now, next thing we're going to talk about related to that kind of is wave speed. Okay. Some of the transverse waves that we've talked about, light, for example, radio waves and so forth, gamma rays, all go at the same speed as long as they're going through the same medium or material. For example, take the speed of light. It could also be called the speed of radio waves. It could be called the speed of gamma rays. It's the same speed. Okay. But technically, the speed of light is the speed of light in a vacuum. If you're in outer space where there's no molecules whatever, then that is technically the speed of light. Once it hits the atmosphere, it slows down. Now, the speed of light is 300 million meters per second, so it might slow down to 299,999,999 meters per second. It does not like if you were sitting there, you'd say, wow, look how that light slowed down when it hit the air. But it's still going really, really fast, but it does slow down a little bit. And if it hits glass, like in a solid, like your glasses, the curve there, it will slow down again when it hits the glass. If it goes to a liquid, water, another liquid, it will slow down or go different speeds, okay, depending on what medium it's passing through. Now, for transverse waves, these are like the electromagnetic waves or rays that we talked about. They're the ones that, first of all, can go through a vacuum. So they go the very fastest when there's nothing, so to speak, to get in their way. And so they go fastest in the vacuum. Then they would go next fastest in gases. Then when they hit liquids, they would slow down. And then when they hit solids, they would slow down even more. Now, just for the record, if something was going into solid, which slows it down, and then it went back into air, it would speed back up to the same speed it was going in the air before it came in. Okay, so, but at any rate, that's the deal. It's very fast in the vacuum, then gases, then liquids, then solids. Now, compressional waves, which are like sound waves, where things vibrate, where the matter vibrates, okay, obviously they're going to vibrate better if the atoms are right next to each other, and therefore they can pass those vibrations faster that way. So they actually go fastest in solids, okay, then in liquids, and then the slowest in gases, okay. And say, well, why do we, and then they don't even go in a vacuum. If there's no matter to vibrate, then they don't go at all. So they're almost exactly the opposite of the transverse waves. Think about it. Someone said, well, why don't we listen through solids? Well, it's hard for a solid to connect to your ear to someone talking because, you know, that's just not going to work. Same way with liquids. Also notice it's not saying necessarily that they make sound better. It's just saying it travels the fastest that way. Okay? All right. So those two are kind of the opposite of each other. Now, sound waves, or the compressional waves, since they're going through the medium, they also depend on the temperature of the medium. If the air is faster, we know the temperature means that the atoms are moving faster, the average kinetic energy, so how fast are they moving? If they're moving faster, then they'll carry those vibrations faster. So sound waves will also travel faster in warmer mediums, like if you had warm air versus cold air. If you had a warm solid versus a cold solid, it's going to affect how fast it carries the sound waves. So that's for the sound waves or compressional. Now, the last thing about those we want to talk about is velocity. There's a formula for the speed or velocity of a wave. All right, and the formula is the velocity of the wave is equal to the wavelength. All right. Now, if you make the wavelength longer, okay, so it's longer between waves, all right, as opposed to a short one, okay, if the speed is the same, then you would have a higher frequency. More of these would have to come by in the same length of time it would take for this one to get by if the speed is the same. That's what we talked about earlier. If the speed is the same, the velocity and wavelength are going to be different. Now, if you have a longer wavelength's longer, and you still have the frequency, which means there's the same number of them going by per second, then that would have to go faster. Okay, so the velocity would have to increase. So if you increase the wavelength and keep the frequency the same, then the velocity would have to increase. Same thing, if you keep the wavelength the same, but they come by more frequently or faster, basically, then the velocity of the wave would have to increase. Okay, so if velocity is the same, then these two, wavelength and frequency, are inverse of each other. But if you increase the wavelength and keep frequency the same, then the velocity would have to increase. If you keep the wavelength the same but increase the frequency, then the speed would have to increase. And you can kind of see how that works. Now, most of the time we're talking about the speed of light through air, and so it's pretty much the same speed all the time. And so that's why we say if the wavelength is bigger, you have an inverse frequency. But keep in mind, since the speed can change, then so could these other factors. All right. The units of the velocity, by the way, are meters per second. Okay, because our wavelength is measured in meters, and frequency is how many come by per second, so wavelengths per second. So meters per second is the units for the velocity of speed. So when we say like the speed of light, we said was 300 million meters per second. That would be its velocity. All right. Now, amplitude we talked about a little bit before. If we talked about just transverse waves, okay, amplitude has to do with how far up above and beyond the resting position it goes. Okay, so if we had these two waves right here, okay, we would say that this one, the first one, has a greater amplitude than this bottom one, because this one does not go up or down very much. Okay, so the more it goes up and down away from the resting position, or that line in the middle, the more amplitude it has. And this is usually how much energy. Think about a slinky. If we're making a slinky go up and down like this, the more energy we put into it, the higher the things are going to be, and the less energy, it's going to have less amplitude. Okay, and so that kind of makes sense. So it is related to how much energy it has. Now, in a compressional wave, remember we said if they're squeezed really close together or really far, that shows great amplitude. If they don't change very much, they just barely squeeze together and they just barely spread apart, that would be low amplitude. So this top one would be violent, and this bottom one would be whispering, because it's just barely compressing the atoms together. Okay, and that would be the amplitude in a compressional wave. Now we're on about Roman numeral 6 on your notes. We're talking about the behavior of waves. Okay, some things about the behavior of waves. First thing a wave can do, object, it's moving through space or through the air and it hits something, is that it can bounce off. If it bounces off, then that is called reflection. When a wave bounces off, it's reflected. Now, if this is our surface, let's just say a mirror, here's our light rays coming in and then it bounces off, okay? And so someone over here could see what's in the mirror because of the light ray bouncing off, okay? The wave coming in is called the incident ray or the incident wave. Waves and rays are kind of used interchangeably, okay? The second one here is a reflected ray or wave. Now, it does not matter whether it's at the bottom or coming off. What matters is the incident ray is coming toward the mirror. The reflected ray is going away from it. We could have one going the other direction, where we have a boom coming in like that, okay, and then it's coming off like this. Okay, in this case, this would be the incident ray, this would be the reflected ray. It really doesn't matter if it's going up or down, it's just whichever one is coming toward the mirror is incident, the one that's bouncing off is reflected. Now, if we were talking about geometry, the word normal, if something's normal to something else, it means it's perpendicular to. So if we drew an imaginary line, dotted line here, it's imaginary, but it's perpendicular to the surface, that's a right angle, all right, that's called the normal. All right, and so an incident ray comes in on one side of the normal and bounces off on the other side. And you will notice that the angle between these two and the normal are the same. The angle on this side between the incident ray and the normal is called the angle of incidence, and the angle, surprisingly enough, on the other side between the normal and the reflected ray is called the angle of reflection. All right, and this law, that this is always true, that they're equal to each other, they always come off at the same angle, is called the law of reflection. When the angle of incidence comes in, it's going to bounce off at the same angle on the other side. It can't come in at this angle and then say on this side come off at a different angle, okay, because that would make this angle more than the angle of incidence. And the law of reflection says no, the angle of incidence is always equal to the law of reflection. All right, and that's one of those things you can count on because it's the law. All right, now another behavior besides reflection is one that we've already talked a lot about when you were in grade school, or at least in junior high, no doubt. And this is the idea of refraction. Okay, refraction is up over here. Okay, refraction. Refraction has to do with a wave bending, as well as does diffraction. We'll talk about it in a minute. But in refraction, you have a wave coming. It hits a medium, a different medium. So say this is a glass lens, the gray shaded part here, or whatever color that is, me being colorblind. But that shaded part is glass. And this is a wave of light moving through air. It's moving through air. It's going straight, boom, boom, boom. But when it hits this, the bottom part of it's going to hit the glass first, and it's going to slow down. The top part's still going to go faster, so it's going to make it turn, and so it slants like this. Now, once it's all in the glass, it's going to all go the same speed again, so it goes on a straight line. But once it gets down here, this time, though, the top of the ray is going to hit the air first and going to speed up, which makes it turn even more, and so it tilts more at an angle here. Same thing happens at the bottom, just in reverse. This time the top hits it and slows down, the bottom speeds up, and so it makes it bend. And when you get here, the bottom speeds up again, and it bends it again. Okay, and eventually you can see how these will cross and focus back here, which we'll talk more of later. But basically, refraction is when a wave bends because it's changing speed, going from one medium, like the air, to another medium, like a solid glass. Okay, and so it makes it change directions because it changes speed as it's going through the medium. This is how glasses basically work to focus, magnifying glasses, things like that, to help focus light. All right, now the last thing we're going to talk about is diffraction. Say I have a wall with a doorway in it here and here. All right, and inside this room I turn on a light bulb. You can see that's not Mr. McMurray's hair, no, although it's getting kind of long and raggedy. All right, this is light coming off. Okay, now, if light could only go in straight rays, it would just make a square over here like so, and that's it. You would just see that little path of light. But what happens is, if you were standing in the room, it would not be completely dark except for that one little place where light came in the door. The light would start to spread out as soon as it gets through there, and it would start spreading out and going around. So even though it would be brightest right around the door and bright this area, as you get farther out, the light's being spread out over a bigger distance, so it'd get dimmer and dimmer, but the light would go around or bend around the corners, and that is called diffraction. All right, diffraction is when light bends, when it goes through an opening and then starts bending out to the sides, or it could be if you had a corner or something like that, and you put a light over here, well, some of the light would bend around the corner, and that is called diffraction. Radio bend around things. If you're in the city, the longer waves, which are like AM radio, will bend better than the small waves, and so you can hear AM stations better because they bend around the buildings better. So the longer the wavelength, the better the wave diffracts. All right, we'll stop right there, and if nothing interferes, we'll be back for part 3 and the last of our wave notes.